Welcome to my 8th class on single random variables. So in this lecture video, we'll be discussing about the fourth application, that is exponential distribution. Application exercise 4. So in this video, we'll be discussing about how to derive mean, variance and standard deviation of exponential distribution, and we'll be expressing the characteristic function in terms of exponential distribution, and we'll be deriving the mean, variance and standard deviation of exponential distribution in terms of characteristic functions. Exponential distribution. A random variable x is called an exponential random variable with parameter lambda is greater than 0, and its probability density function is given by fx of x is equal to lambda into e power minus lambda x for x is greater than 0 and it is 0 otherwise. So now the corresponding CDF I'm going to find. The corresponding cumulative distribution function of the random variable x is given by fx of x is equal to 1 minus e power minus lambda x for x is greater than or equal to 0 and it is 0 otherwise. So now since here this x is a continuous random variable, to derive this CDF I am going to integrate the density function what they have given between the limits minus infinity to plus x. The formula is given by fx of x is equal to p of x less than or equal to x is equal to integration minus infinity to x fx of x dx. So now in this place of density function, I am going to replace the given density function lambda into e power minus lambda x with the limit x from 0 to infinity. So I'll be getting the expression fx of x is equal to integration 0 to x lambda e power minus lambda x dx. So since here lambda is a constant, I can take lambda outside. Integrating e power minus lambda x, we got e power minus lambda x by minus lambda between the limit 0 to x. Now if I apply the upper limit, I'll be getting e power minus lambda x plus 0. So since I cancelled lambda here, and since I'm having 1 by minus here, so it will become minus e power minus lambda x plus e power 0 after applying the limit. So now it will be equal to 1 minus e power minus lambda x. So hence we got the cumulative distribution function as 1 minus e power minus lambda x for x is greater than or equal to 0 and it is 0 for x is less than 0. So now the graphical representation of the probability density function and cumulative distribution function for the exponential distribution. So since here since the PDF is an exponential distribution, the curve will be in the exponential form only. The PDF plot is given like this. So this is a graphical representation of exponential distribution for probability density function, and this one is the CDF plot for the exponential distribution. So now I'm going to derive the mean, variance and standard deviation of the exponential distribution. The first thing is I'm going to consider the PDF of exponential distribution. So we have the expression fx of x is equal to lambda e power minus lambda x for x is greater than 0 and the function will be 0 otherwise. So since here the x is a continuous random variable, I'm going to use the mean formula in terms of continuous random variable only. That is expectation of x is equal to integration minus infinity to plus infinity x into fx of x dx. So in the place of density function, I'm going to use the function lambda into e power minus lambda x between the limit 0 to infinity. So I'll be getting the expression like expectation of x is equal to integration 0 to infinity x into lambda e power minus lambda x dx. I got it. So since here the lambda is a constant, I can take lambda outside. I got the expression like lambda into integration 0 to infinity x into e power minus lambda x dx. So now to integrate this equation, I am going to use the Bernoullis condition. So here I'll be treating the x term as an algebraic term, that is u, and the exponential term as v. I'm going to use the Bernoullis condition now. So it will be equal to expectation of x is equal to lambda I'm keeping as it is. So first I'm keeping u term as it is. Integrating v function, I got e power minus lambda x by minus lambda minus 1 into this one in the sense differentiating the u function, I got 1 here Now again integrating this v function, I got e power minus lambda x by minus lambda whole square between the limit 0 to infinity. So I'm keeping lambda as it is. So since we know that the value of e power minus infinity is 0, the entire function is consisting of e power minus lambda x. Suppose if I apply the upper limit infinity, the complete equation will become in terms of e power minus infinity. So it will become 0. So I'm putting 0 directly for the upper limit. And for the lower limit, the first term containing x variable, if I put x is equal to 0 here, the first term will become 0 minus the next function will become e power 0 by minus lambda whole square. On simplifying this expression, we'll be having lambda into 1 by lambda square. One lambda gets cancelled. I got expectation of x is equal to 1 by lambda. So now I'm going to find expectation of x square. To find expectation of x square, the formula is integration minus infinity to plus infinity x square fx of x dx. So now same thing here also. In the place of density function, I'm going to replace fx of x is equal to lambda e power minus lambda x with the limit x from 0 to infinity. So the equation leads to expectation of x square is equal to integration 0 to infinity x square lambda e power minus lambda x dx. So since here lambda is a constant, I am taking lambda outside. Integration 0 to infinity x square e power minus lambda x dx, we got it. So now I'll be integrating this function by using Bernoullis condition. So I'm going to treat x square as u and e power minus lambda x as v. I'm going to use Bernoullis condition now. So now expectation of x square will become lambda into, I'm keeping u term as it is, integrating v function, I got e power minus lambda x by minus lambda minus differentiating u function, I got 2x, and again integrating v function, I got e power minus lambda x by minus lambda whole square plus differentiating u function again, I got plus 2. And integrating v function again, I got e power minus lambda x by minus lambda whole cube between the limit 0 to infinity. So now again the entire function containing e power minus lambda x, if I apply upper limit, the entire equation will be of the form of e power minus infinity only. So I can put directly 0 for the upper limit. And the first two terms containing the x variable, suppose if I replace the lower limit 0, the first two terms will become 0. So I am writing 0 directly. And the third term will become 2 times of e power 0 by minus lambda cube. It will become 2 lambda by lambda square. So one lambda gets cancelled. I got the expectation of x square is equal to 2 by lambda square. Now variance. To find the variance, the formula is given by sigma x square is equal to expectation of x square minus expectation of x whole square is equal to 2 by lambda square minus 1 by lambda whole square. By simplifying this, we'll be getting 2 by lambda square minus 1 by lambda square. So it will be equal to 2 minus 1 by lambda square. It will be further equal to variance is 1 by lambda square. The standard deviation is given by square root of variance. So the standard deviation is 1 by lambda. So now I'm going to derive the exponential distribution in terms of characteristic function. So to derive this one, so first take the density function of an exponential distribution, that is fx of x is equal to lambda e power minus lambda x for x is greater than 0 and it is 0 otherwise. So first now let me consider the characteristic function in terms of continuous random variable, that is xi x of omega is equal to expectation of e power j omega x integration minus infinity to plus infinity e power j omega x fx of x dx. So since here x is a continuous random variable, so I am using the continuous random variable case. So now I'll be replacing the density function fx of x is equal to lambda into e power minus lambda x along with the limit 0 to infinity. So we got the expression like xi x of omega is equal to integration 0 to infinity e power j omega x lambda into e power minus lambda x dx. So since lambda is a constant, I am taking lambda outside, integration 0 to infinity. So here bases are same, I can add powers. So it will become e power j omega x minus lambda x. So I'm taking minus and x common factor. So I got the expression like e power minus of lambda minus j omega x. Why? Because after applying the upper limit, it will become e power minus infinity. So I can put directly 0. So I got the expression like now lambda into integration 0 to infinity e power minus of lambda minus j omega x dx. Like after integration I got the expression like lambda into e power minus lambda minus j omega x divided by minus of lambda minus j omega at the limit 0 to infinity. So for upper limit it will become 0. For the lower limit we got the expression like lambda into e power 0 by minus of lambda minus j omega. So the characteristic function will be lambda divided by lambda minus j omega. To check the function is true or not, I'm going to put omega is equal to 0. Like after putting omega is equal to 0, we got the expression like xi x of 0 is equal to lambda by lambda minus 0. It will be equal to xi x of omega is equal to 1. So hence the obtained expression is true for the exponential distribution. So now I am going to derive mean, variance and standard deviation of the exponential distribution in terms of characteristic function. So to prove this one, I am taking the exponential distribution in terms of characteristic function only. That is given by xi x of omega is equal to lambda by lambda minus j omega. Okay, to find the expectation or mean value, the formula is given by d by dj omega of xi x of omega to omega is equal to 0. So now I am going to replace the characteristic function xi x of omega lambda is equal to lambda minus j omega here. So now it will become expectation of x is equal to d by d j omega of lambda by lambda minus j omega at omega is equal to 0. So now I will be differentiating this expression for j omega by using quotient rule. So I'll be getting 0 minus lambda into minus 1 by lambda minus j omega whole square at omega is equal to 0. So now if I replace omega is equal to 0 here, it will become lambda by lambda minus 0 whole square. The expectation of x will be equal to 1 by lambda. So now I'm going to find expectation of x square. It is given by d square by dj omega whole square at xi x of omega is at xi x of omega at omega is equal to 0. So now it will become what? Expectation of x square is equal to d square by dj omega whole square. I'm replacing xi x of omega here. I'll be getting lambda by lambda minus j omega at omega is equal to 0. Now it will be equal to d by dj omega. In the first time, differentiating the first time by lambda by lambda minus j omega by using quotient rule, we got d by d j omega of lambda by lambda minus j omega at omega is equal to 0. Now again differentiating this function with respect to j omega by using quotient rule, I got the expression like 0 minus 2 lambda into lambda minus j omega into minus 1 by lambda minus j omega whole power 4 at omega is equal to 0. So now, like after simplifying this, we got 2 lambda by lambda minus j omega whole cube at omega is equal to 0. If I replace omega is equal to 0, I got the expression like 2 by lambda square. So now we can find the variance. So once we got the expectation of x as 1 by lambda and expectation of x square is 2 by lambda square, we can find the variance. So the variance is given by expectation of x square minus expectation of x whole square. We got 2 by lambda square minus 1 by lambda whole square. It will be equal to 2 by lambda square minus 1 by lambda square, or 2 minus lambda by lambda square. I got the variance is equal to 1 by lambda square. Now finally standard deviation, it is given by square root of variance. So I got the standard deviation is equal to 1 by lambda for the exponential distribution. Okay, in the next lecture video, I'll be discussing about the fifth application, that is Gaussian distribution. Thank you.